stuff. I'm especially in the beginning going to view this more as a setting the stage for how people tend to think about distributed multi-robot systems. And in particular, I'm going to talk a little bit about how we're using graph theory for thinking about distributed algorithms. And then I'm going to move on to tailor these graph theoretic ideas for multi-robot systems. And finally, I'm going to look at, okay, so now let's say you have a collection of these and you have a joystick, a million mosquitoes and a joystick. What do you do with a joystick? So basically, how do you actually inject influence onto large collections of robots? And I want to start with a mood picture. Multiple reasons for this. This was ICRA 2009. So this is the main robotics conference, and I was kind of proud of this because this was 5 robots doing something non-trivial. Two of them were supposed to have GPS. They're supposed to get to an area. These are supposed to basically be dragged to this area, and then once they get there, they're supposed to build a certain geometric shape. And no one is supposed to know in advance where they need to be in the shape, so they need to figure out what role should it take on in the shape. We were using something called graph grammars to define local rules for how they should assemble. And in fact, this was part of a NASA project where we were supposed to instrument the polar ice caps by deploying various kinds of sensors onto these polar ice caps, and they were supposed to do something like this. Unfortunately, so we had funding to go to Antarctica, which was great, until NASA discovered a glacier in Colorado and said, you can go to Colorado instead. So these guys never made it to Antarctica. The point with this video, though, is that it has 5 robots, and I was a little bit proud of this when I gave the talk at ICRA. After me, this guy, Alkerio Martinoli from EPFL in Lausanne, in Switzerland, started with this video. By the way, I was 5 robots. I'm very proud. This guy had 278 robots. These 278 robots, none of the robots are talking to each other. None of them have localization, meaning no one knows where they are globally. All the robots are doing is they're locally measuring the relative displacements between themselves and their neighbors. None of the robots have a pre-assigned role in what they're supposed to do. And I was sitting where Steve is right now, sweating, because this was beginning to be really nerve-wracking. And it's unreal, actually, how good it is. It's absolutely remarkable. In fact, I was feeling strongly that I should not, to be honest, have a job anymore, because everything I want to do was solved. In fact, like I said, it's unreal. So here is the little caveat, though. So everything I said is true. These are, I will talk to you in a sec, Daniel. There's no localization. There's no communication. There are no pre-assigned roles. But there was a tiny little trick that was going on there. So does anyone know what the answer to the trick is?
I don't want to ruin it for everybody.
Okay, I'm going to ruin it for everybody now. So what they did is that they took 278 graduate students. Each graduate student, they placed the robots perfectly in formation, had the robots do random stuff, and then they ran the video backwards. So what you saw there was a backwards multi-agent robotics thing. But the genius of this video, I think, apart from the fact that I still have a job because we can't do this forward in time, is this is exactly the problem in multi-agent robotics. What you want is with very little information, typically sensing information, no typically pre-assigned roles, have the robots figure out where they should be, assemble this geometric structure that they're interested in, and move from there. So now, yes, Daniel. So if I hadn't badmouthed them about, so they're not saying in the video that it's backwards, right? They're not paying me anything. But yeah, okay, fine. Good. So that's good because this is a nice mood picture because that's what we want to do. We want to do EPFL forward in time, 278 robots, which we can't. I should say that. And what I'm going to talk about today is multi-agent robotics. But a lot of the stuff that I do is also applicable to a number of other domains. So, sensing and communication networks, even biological networks. But the main point is what I want to do is I want to control, using local rules, some geometric shapes. And in robotics, we typically think about formation control. So how do you get into a certain type of formation? How do you get into a certain type of geometrically defined shape? So for instance, if you have these coordinated control problems, they're actually the same. You get space mirrors to line up in a proper way so that you can get better photographs. When you talk about sensor and communication networks, typically there, the specification is not so much a given target shape, but you want the geometries to satisfy certain things, like you want to achieve coverage in the sensor case, or you want to achieve coverage while ensuring connectivity of the network. Some of these biological problems turns out to be geometrically defined as well. You have stem cells that you want to turn into muscle tissue. So what do you have to do? You have to fold them in certain ways to express certain genes, which is also can be thought of as a geometric network control problem. So I'm going to be thinking about geometric problems. So how do you get these nodes to form certain geometries? And dealing with multi-agent robotics, you're actually violating the oath of the office if you don't show a picture of animals. So here's the mandatory bio slide. And this is not just a mandatory bio slide. We have learned a lot about multi-agent robotics by going to nature. And in fact, it's more than just inspiration, because one of the few places where we have successful collections of individuals doing interesting things together is in biology. So people have looked to biology for inspiration, but also we have technically learned a lot. There are people like Ian Cousin at Princeton or Danny Greenbaum at University of Washington that have spent a lot of time writing down differential equations that govern how fish or birds, or Stephen Pratt at Arizona State, how ants coordinate. And these kinds of algorithms have actually found their way into multi-agent robotics in a rather, I think, remarkable question. So the first things that we need to understand is really how should we control these systems? So what are the right models for even describing a team of robots? And in particular, should we worry about individuals? Clearly, if you have 1 million robot mosquitoes, individuals don't matter. But sometimes we need to worry about the individuals. And how do we take that into account? And in fact, I started working on multi-agent robotics coming from a biological perspective. Because I had a tank of ants. This is 2002. Actually, it's 2001. I had a tank of ants. The ants were moving around. I had an overhead camera tracking what the ants were doing. So here's what the ants are doing. This guy is squished, it's not moving, but the others are doing some stuff, and they seem to be meeting each other. And what I wanted was purely from the video and a model of the ant dynamics, they were unicycles in this case, produce control laws that describe what the ants are doing. Not trajectory level, but I actually wanted to find controllers, and in this case they had to be hybrid controllers, that were consistent with what the ants were doing. And we worked on that, and I wanted to put this automatically on the robots. I wanted to be able to go from a video of ants onto robots that were actually doing it. I'm not going to show you a simulation, because we never put it on the robots for reasons that will become apparent. This is a completely different number of simulated ants, different initial conditions, simulating the controllers we grabbed automatically. And one thing you see is that they tend to cluster together a little bit more than the real ants, and they actually go through each other, which real ants don't. You can fix that by adding avoidance terms and stuff, but then you're cheating. Then you're adding things that the ants didn't tell you. So I didn't want to put this on the robots because it wasn't perfect. And in fact, it wasn't even clear if I could declare success or not on this, if I had successfully mimicked the ants. Stephen Pratt, the ant guy at ASU, he looked at this video once and said, kind of looks like ants. And that was the validation I took and said, okay, good, I'm done. And I'm now going to tell you why I consider this a failure, meaning what was hard about this. What was hard about this was, here's an ant. The way the ants interact with other ants is basically they have these mandibles, which are these glorified antennas, and they basically can sense with their mandibles this little wedge region here. And what my controllers had to do is I had to spend so much effort keeping track of who was in my wedge, and are you in this side of the wedge? Where is your wedge relative to my wedge? So the controllers became very, very, very complex because I had to worry about wedge intersections and where are the wedges. And basically, I think this is the key reason why I failed. Here's another reason why this wedge view of the world is not very good. These are 3 robots, cartoons of robots. Here is a robot with a omnidirectional range sensor. So this would be an IR or a sonar ring, for instance. What this robot can see, idealized, is a disk right around it. Here's a robot with a camera. It can see this wedge, possibly very far away. And here's my cartoon of a robot that has a radar array. You get these characteristic flower-type patterns. If I have to design control strategies that worries about, where is this geometry and where is this guy relative to that guy, I'm doomed to failure because I'm just going to spend all my time tracking where the little petals in the radar array is. So instead, what one needs to do to be able to successfully think about these problems is to say, forget about the geometry. It's too hard. What I'm going to say here is that this guy can see that guy. Well, I'm just going to say there's an edge between them, and information is flowing in this direction. This guy can see that guy. Well, the information is flowing in that direction. Now I have a graph. So now I have nodes and edges, and the edges encode information flow. And what I'm going to do, and what people have done for the last 10 years, is design distributed algorithms on graphs. And then you have to make assumptions about the graphs and assumptions about the topology of the graph that make your algorithms work. And then what you have to do is go back and make sure that the actual sensor configurations support the graph assumptions. So for instance, an assumption can be that you have a path like this, weakly connected directed graph. Well, if you need that, you better make sure that your sensing strategy can support this, at least sometimes. So you can actually go from the algorithms defined on graphs back to the sensors and actually make sure that your sensor structures support the information flow that you want. So my claim is that the graph is really the right object when you're going to think about distributed multi-robot algorithms. And this is not my controversial claim. This is mainstream multi-agent robotics. And in fact, the way you connect graphs to the underlying geometry of the sensors, well, you can define these different kinds of proximity graphs. So for instance, a delta disk graph, or a disk graph, is a graph where everyone has a footprint. There are other kinds of graphs. Delaunay graphs are something you get in sensor networks where you basically divide the region into Voronoi cells, and if cells are adjacent, there's an edge between them in the graph. And this is a graph that basically describes coverage problems. Visibility graphs, you have a camera, and can you see? In communications, Gabriel graphs shows up all the time, where you basically have a disk plus long-range interactions. So these are different ways in which one can geometrically encode the information about the nodes into graphs. And I should point out that in this talk, I'm actually adding references. I didn't know if the slides would be made available afterwards or not. In case they are, I put them there just so you can look up where these things come from. So an example, right, is a delta disk graph here, where you have nodes. This is robot 1, position at x1, and it can see this graph. Now, if you're intersecting the graph, then you have an edge. So I'm just going to lift this and say, hey, this is my graph structure in this case. So this is how you go from geometry to combinatorics, or topology. Good. OK, so having said that, this is now how we're going to think about this problem. This is me. I'm node I. This is my state. In the robotic case, this is position typically, but it could be other things. It could be some sensor that's measuring something. Now, these are my neighbors, right? So this is my neighborhood set at time k. I'm going to be able to have information available from my neighbors. I'm going to look at directed edges as flowing in the direction of the edge. So at time k, if I can measure, for instance, relative position, this would be if I'm having sensors, I can typically, I don't know where you are exactly, but I can measure where you are relative to me. So I can measure maybe this. If I'm allowed to talk and we have a common reference frame, you can actually tell me where you are or what your abstract state value is, for instance. So depending on what kind of information you're flowing, you can either have something like knowing the state of your neighbors, or at least the relative distance. And what we're interested in is really finding update rules. So how do I update the position or the state of node I or robot I using my information and the neighborhood information? I'm mainly going to deal with it in continuous time, but this is really the control problem. How do you pick these f sub i's in an interesting way? So we're going to start with the world's easiest multi-robot problem. This is known as the rendezvous problem, and it's canonical in the sense that if you can solve that, we can solve a lot of other problems. And How many people know about the rendezvous problem here? Oh, yeah, good. So a third. So I'm going to speak to the other 2/3 here. You and I are fairly unintelligent robots. We're supposed to meet at the common location. And I can measure with my sensors where you are relative to me. So I can measure this. I know where you are. I don't know if I'm in Georgia or in Illinois. I don't care if you're in Georgia or Illinois. But I know that you're there. You know that I'm here. How should we move in order to meet halfway? Or meet somewhere? We don't care where we meet, because we don't know where we are, but we need to meet at the same place. Which direction should we go in? Okay, I know that you're in that direction. Should I go there? No, that seems ridiculous, right? We should walk towards each other, right? So here is a canonical idea. This is me. I'm moving towards you, and this is how fast I happen to be running. This is my gain. This is you. You're going towards me. Maybe slower or faster. I don't know. And if we have the same gain, we should meet halfway, right? It seems completely reasonable to do this. Good. So now let's involve more people in the mixer. So now we have, this is still me, and this is you. Yeah. Okay, fine. Which direction should I go in? I want to meet now my neighbors in a common location, and I can measure where they are relative to me. Okay, it seems ridiculous to go in that direction, right? It seems ridiculous. It should move somehow to where they are. For instance, I can define the center of mass of my neighbors and go towards that. That seems completely reasonable. And in fact, anything else seems borderline strange. Whoops. So this is what I'm going to do. I'm going to compute where the center of mass is of my neighbors and go in that direction. And in fact, it turns out I can do this very, very simply. It's the same equation that we just came up with. I just sum up all of these contributions. It's going to give me a point that's somewhere over here. And it's not the center of mass, but direction is through the center of mass. And that's all that matters, right? That we're going in the right direction. So by doing that, I would get this kind of update law. And in fact, this is known as the consensus equation. It's become giant because it works. In fact, what it does is the following. If you have an undirected graph, meaning if I can see you, you can see me, and the graph doesn't change, which is obviously a lie in a robotic setting, but if the graph is static, then this consensus equation achieves consensus, meaning everyone meets at the same point, in fact, if and only if the graph is connected. I mean, there's a path between every player. And in fact, you actually end up on the initial centroid. So the centroid is preserving. And here is now an example of a topological condition on the graph, saying the graph has to be connected, that we now can lift back onto our actual sensors and ensure that this is the case. So here's a video of this happening where they run the consensus equation. They all collapse down on the same point.
But this will work only if there are no obstacles.
Absolutely. At this point, there are no obstacles. There's nothing interesting.
In Georgia and Illinois, the example was not good.
No, the example is fantastic because the point with the example was I don't know where I am. Right? And she doesn't know, but I can still see her. So the example would be no good if that guy was in between us and we would actually...
Georgia, Illinois, there will be something in between.
But the assumption was that I see where she is, right? I don't know if this auditorium is in Georgia or Illinois, but still this is a great example. But point being, this is not, so we're just doing push-ups right now. We haven't actually started to do any, yeah. So how do we actually show this? Well, we need some tools, and the tools are found in algebraic graph theory. Whenever you say algebraic anything, what it means is that you're associating mathematical objects to the thing you're studying that you can manipulate algebraically, matrices. And for graphs, we have some standard matrices. You can take the degree of each node, which is the number of neighbors, and form a diagonal matrix known as the degree matrix. The adjacency matrix just basically encodes whether or not two nodes are neighbors. You have some directed version of it. The reason why you need these matrices is that there's something called the graph Laplacian, which is the degree matrix minus the adjacency matrix. And it's a fantastic matrix. And the reason it's fantastic is for the following reason. If I have this consensus equation, the gammas are 1 now, so there are no weights or no gains. Then if I stack all my states together, assuming that they're scalars, but you can do this in higher dimension as well, I get x dot is minus the Laplacian x. And this is the world's simplest system, right? This is x dot is ax, linear system theory, right? All you need to know about the system is hidden inside this matrix X, L. Everything you need to be able to understand what the system is doing is by looking at L. And in fact, what you need to know is what the eigenvalues are, what the eigenvectors are. So for instance, if the real part of the eigenvalues of minus L were all negative, this would be an asymptotically stable system. We don't expect asymptotic stability because that means we all end up at the origin, and the origin happens to be in Atlanta. So if we all did this, we would all go to Atlanta because there are no obstacles in between here and Atlanta, which is not what's going to happen. We're going to meet here. If it had an eigenvalue with a positive real component, then we would blow up, and that doesn't seem likely. So we're probably going to end up somewhere in between. And in fact, this Laplacian has something very nice going for it. So it's positive semi-definite, which means all the eigenvalues are real and non-negative. And in fact, if and only if the graph is connected, it has exactly one zero eigenvalue, and all the other eigenvalues of L are positive. So minus L are negative, which is important. The other thing that's important is we know exactly what the null space looks like, meaning the null space to L and its span of this vector with just a bunch of ones. It's 1, 1, 1, 1, 1, 1, 1. So first of all, one thing that we know about systems like this is if you have one zero eigenvalue and the rest are negative, then what you're going to do is asymptotically end up inside the null space. So here's some cartoon of what's going on. Well, so when we run the consensus equation, we're all going to end up inside the null space, which is 1, 1, 1, 1, 1, 1, 1. And every component is an individual's position. So everyone is going to be at the same location. That's how you would show that this thing, in fact, solves the consensus problem. So now, by looking at the spectral properties, the eigenvalues and the eigenvectors of the Laplacian, we know when this thing works. Cool, huh? Now, you can immediately apply this to other problems. So here's the formation control problem in robotics. This is where all the robots are. Here are target positions. We're here in Illinois. I drew a picture of what I want you guys to look like, but I did it in Atlanta and I forgot to bring it. So what I'm OK with is, as long as we get into any translated version of these target positions, we're OK. Because we don't need to be in Atlanta. We need to be in Illinois. And then you can immediately run the consensus equation on the error. So where am I relative to my target position? I get the consensus equation on the errors. And I know that asymptotically, if the graph is connected, you have a constant translation of the target positions. And you can actually immediately turn this into controllers on the robots. So what you have is you have a constant translation of the target positions. So you can use this way more than, immediately use it to more than just meeting at the middle. So here's an example of this. Here we're also agreeing on rotations. So it's translation and rotation. And these are 15 robots. We're the GRITS lab, so they're actually told, we're broadcasting every now and then, go produce a G. And then produce an R. So what they need to do is figure out what's the translation and what's the rotation of this formation. What they're also doing is solving what's called the assignment problem, but it's not that important, meaning who goes where. But this is basically just the consensus equation in action. The robots aren't talking, but I do have an overhead tracking. In theory, they could know everything about everyone, but they don't. We're actually restricting the information they're allowed to act upon. I think this is forward. It doesn't matter, right? Because we're going through the alphabet. We would just spell GRITS backwards. This is cool, though. So now we're starting to mess with it, and we can still do it. 100,000 hits on YouTube, I may add, this thing. Yeah. So one thing you should know is every self-respecting robotics lab needs a spiffy acronym. And when I started at Georgia Tech, I taught this undergraduate robotics course. And one of the first homeworks was to come up with an acronym for the lab. And then the students got to vote on it. And GRITS won. I had the veto power, and I didn't veto that. But yeah. But this has gone out of control. We have software packages called muesli and pancakes. And we have so the breakfast theme is everywhere. Anyway, so we can do things like this using things like the consensus equation. One thing one should say about this Laplacian, though, is that this second smallest eigenvalue is super important. Because what it's going to tell you is really this, that the rate of convergence is exponential in this eigenvalue. So the higher lambda 2 is, the faster the thing will converge. And in fact, the best you can do is to have, well, so another thing I should say is that lambda 2 is related to what's called the algebraic, well, it is the algebraic connectivity, which is related to how densely connected the network is. So if everyone here were to know everything about everyone else, we would converge very quickly. But then we would have to either talk a lot or see a lot. So there is a fundamental trade-off in general between these distributed algorithms in terms of the information needed to support the algorithm and the convergence rate. And in fact, if you have a complete graph, which is the fastest you can do, which is basically the centralized case, the thing is fast. Right? You have lambda 2 is equal to n, which is the number of neighbors. If you have something like a star graph, then all of a sudden the convergence rate drops dramatically, because this is a much less connected network. What you can see is you can, for instance, take one node and you completely disconnect the network. So here you have less communication, but at the same time you have way slower convergence. And the worst thing you could possibly do is a line from a convergence rate point of view. So lines are useless if you want to be fast, but they're nice because they don't require lots of communication, for instance. OK, good. So what did I claim? Well, the consensus equation will drive the node states to the same value if the graph is static and connected. I should point out, though, that I'm by no means taking credit for the consensus equation. People are arguing over who was first. My bet is on John Tzitziklis, but it's not entirely clear, but certainly not me. What I do want to point out, though, is that this situation that I described with static graphs, undirected edges, is clearly not a reasonable assumption in robotic networks, because I'm going to be moving around. Sometimes I'm going to see you, and then I'm not going to see you. And you may have a different sensor, and you may see me without me seeing you. So you have to be more careful about how you actually deal with the edges. And if you have communications, there are communication failures that you typically want to model as random link failures as well. So you're going to have these random components into your edges. But the point is that if you have now much more elaborate graphs, you can't look at eigenvalues all of a sudden. You have to be a little bit more creative. But it turns out that you can actually fairly easy do this hybrid Lyapunov function technique. And I have a reference in here if you want to look at it. But the point is that we can actually show theorems for these switched graphs as well, where edges come and go. And here's a nice theorem. As long as the graph stays connected, so edges can come and go, but as long as the graph is connected, then this equation, the consensus equation we talked about, will still drive all the agents to the same state value. So it still works in the switched case, which is nice, because in robotics there's no guarantee that we're going to have these edges. So here's the same video again, and what you're seeing there is that this is actually a delta disk graph where edges come and go as agents get closer, and the convergence rate speeds up towards the end, right? Because towards the end you have a complete graph. But this is nice, because now what I need to do when I design my robotic algorithms is to come up with sensing strategies that support connectivity. And you can actually come up with a weaker version of this theorem that says that as long as the union of the graphs you have, there is a time window so that the union, no matter what time it is, the union of the graph is connected. Which means that what you need to do every now and then if you have a camera is just rotate to make sure that you see. If one person has a camera and rotates every now and then, that's a strategy that ensures connectivity in this joint connectivity sense. So that's a strategy that guarantees to satisfy the conditions of the theorem. Now, I promised, or I told you that the consensus equation is still just I call it a canonical problem. And it's canonical because with the consensus equation, we can solve a lot of different problems. The most standard way is to simply throw in weights, nonlinear weights. And people have done this for avoiding collisions, for instance, for doing sensor coverage, for doing connectivity maintenance. So for instance, we know that we need to maintain connectivity. One thing you can do is just crank up the weight as you get close to getting disconnected, so you pay more attention to edges that are about to break. And I have two videos that I want to share with you. The first one is, I think it's mid to late 1980s, done by Craig Reynolds, who's an animator who was working for The Lion King. And he had this problem of animating stampeding wildebeests. and he didn't want to handwrite them or hand draw them. So he came up with these rules that are now known as Reynolds-Boyds for aligning. So you had to align with your neighbors, which is consensus on the heading. So it's just agreeing on the heading. Then he had something that he called cohesion, meaning that the thing didn't break apart. Consensus with a nonlinear term that says I only care when you're close enough, I don't care. And then he also had collision avoidance that made sure that you don't slam into each other, which is another nonlinear weight that pulls them apart. And then he added a little bit of noise to make it look, wilder beastie. So here's Simba, right? And here they come, Reynolds-Boyds. This is a weighted consensus equation in action. It is cool, right? Plus noise. I wish my MATLAB plots looked as good as this, but. Okay, here's another example of a weighted consensus equation. This is not mine. This is from Jorge Cortes and Sonia Martinez's work on coverage control. But the problem there is to distribute agents across an area, and you can actually write this down as a weighted consensus problem. And what's going on there is that you have different densities of interesting things going on, and you basically want to form a good coverage so that you have your nodes, your sensor nodes, more densely packed where there are more interesting things going on. So you can do that as well with consensus equations on steroids. And the weights you can actually choose in a rather straightforward way. So for instance, you can define something like an edge tension on each edge and then say, you know what, if I'm interested in maintaining connectivity, I let this edge tension be high when it's close to cutting off. Or if I want to do formation control, for instance, so I want agents I and j to be close to dij away from each other, then I let this thing have a local minimum there, or in fact a global minimum there. And then if I take the partial derivative of this with respect to xi, I always get something like this. And in fact, what I do is I simply run a gradient descent on this. So I let x dot I be minus this, which now immediately becomes a weighted consensus equation. And the nice thing about this is that the total time derivative of the energy, the total energy in the system is always non-positive. So you know that the energy is non-decreasing. This is a weakly Lyapunov function, and what you use is you use Lassalle's invariance principle to show that the properties you want emerge. But this is the recipe for producing nonlinear weights in a straightforward way. And in fact, I want to show you a video that I'm very, very proud of. I'm teaching this course on multi-agent robotics, and last year, the final project in the course was you were supposed to deploy a bunch of robots on an asteroid, and the robots could only sense the relative displacement from each other, except one particularly clever leader robot that could sense the relative displacement between itself and the next waypoint. And they had to negotiate a bunch of things. One thing they had to do is they had to ensure that they're always staying together, don't drive into obstacles, and everything is local measurements here, except the fact that this guy knows where the next waypoint is. And I'm really excited about this, because this is, it's an exercise in tuning weights, but it's fantastic because it's more complex than most things you'll find at a conference on multi-agent systems. Here they had to switch to one of these coverage algorithms because there were other agents that were dropped randomly in some area, and they needed to make sure that they could actually cover this area. Now, I said you had to do what was called a split and merge behavior. So what this means, you have to separate the network into pieces. Only this guy knows where he's going, so these guys here have to execute an open loop component. And then towards the end, they had to get information. So this was, every time you hit a new waypoint, you have to basically come up with different weights. That's what this exercise was, but it looks wonderful.
If they were wildebeest instead of circles.
That would be nicer, no?
Yeah.
So I turned off the volume, but I'm actually playing the Star Wars theme music in the background. And the music wouldn't work if I... Let's turn on them. This wouldn't work with wildebeests at all, right? So I start with the music, and then I do the science. OK. And here's another example of coverage control that I did with Eric Clavins, where basically you start with a seed. You make sure that you perform these triangles by basically ensuring that you have the right number of neighbors at a certain distance, and then you just propagate these things out through the network. And at the end, you end up with perfect triangulations using weighted consensus equations. So you can do this for a lot of different things with with not too much overhead. So, having said that, now what do we do? The point, what I mean by that is that we're fairly good at designing algorithms that can do particular things, like getting information, coverage in area, surveillance, which means don't cover an area but sweep an area. You can do perimeter control, where you make sure that you distribute things along the perimeter. You have algorithms for flowing along fields. For instance, you're throwing out, in theory, floating robots off the Gulf Coast, and you're tracking an oil spill, for instance, the curve of an oil, or the front of an oil spill. So we can do a lot of things. One thing that I'm really fascinated by is the following. Okay, I've deployed, so now we're going back to the Atlanta or the Georgia-Illinois confusion. I deployed 1 million robots on campus at Georgia Tech because I knew I was going to give this talk and I wanted to show them off. And then I realized that, you know what? The talk is actually in Illinois. Now I have 1 million robots that I need to somehow get to Illinois, which is far and there are obstacles. But the biggest problem there is I don't particularly want to go and reprogram every robot. In fact, what I would like to do is somehow be able to inject new information into this network in such a way that I can control it. And in fact, I'm working hard to make people talk about HSI. So we know HCI, which is human-computer interaction, HRI, which is human-robot interaction. I like HSI, which is human-swarm interaction. And I'm not talking about situational awareness and the psychological effects of having lots of things around you, but fundamentally, how do you interact with lots of dynamical networked units? And it turns out that this is really, really, really hard. I ran simulated user studies where I basically had a bunch of robots, simulated robots, and people trying to control them. We're useless at controlling large collections of things because the network makes everything so much harder. And in fact, as you will see in a bit, I had to go somewhere else for inspiration. But what I'm going to be doing is I'm going to be doing active control of leader nodes. So I'm going to pick a subset of the nodes as the nodes that I'm interacting with and have whatever I'm doing to those nodes, that information propagate through the network. And here is my inspiration, sheep herding. This was the closest I could find in nature of people trying to control really large collections of things. So this is me. I'm trying to, so you guys. Very talented sheep, no doubt. And what I want to do is I want everyone to change places with each other. I want all the left-handed people on this side and all the right-handed people on that side. And what I want to do is I want to pick my 2 deputies, 2 of you, and I want to move you around so that everyone else, thanks to the movements of you, somehow separates into left and right-handed people. That's the problem I'm interested in. And here, what I'm going to do is I'm going to point my joystick at some leaders and hopefully make everyone else follow along with it. That's my take on the human swarm interaction problem. And I need to start by showing this video about, this is the coolest thing about the internet, right? You can find anything. These are a bunch of Scottish shepherds with too much time on their hands. Has not too much to do with this talk, except this is again showing what I want to do with my robots. They have an insane number of sheep. What they're doing is that they're yelling out to the herding dogs, and the herding dogs are producing these geometric formations that I mean, in fact, one thing that I want to do is do this with robots. White sheep and black sheep. It's absolutely insane, actually. Okay, so as if this wasn't crazy enough, now they take them back, they instrument the sheep with LEDs, and then they take them out again in the middle of the night. So these are, I think this is like a 15-minute long video. So if you go to extreme sheep herding on YouTube, you get this. It's so cool what's going on there. And the idea is exactly right. You have these leader nodes that are interacting with the rest of the nodes. So I thought I had a fun job. These guys actually have a... Oh yeah, so this goes on. Yeah, and I can't imagine what the IRB would look like. I don't think the shepherds had to do it, though. They didn't have to go through a full IRB, which was probably good for them. Now, the thing about sheep, though, and it turns out that, so I gave something like, a talk like this in Budapest, and this, I kid you not, Hungarian shepherd came up to me afterwards and said, this is good, but the dogs are not the only leaders. You also have senior female sheep that tend to set the tone for where the herd is going. And it turns out that the leader sheep are pulling the rest, but the dogs are really pushing, so you have to flip the sign in the interaction law. But the math still goes through whether or not you flip the sign. But you have really two modes of interaction when you're herding sheep, the pulling and pushing. And you typically control the pushing, and then the pulling is done by this wise sheep. So there's a pulling sheep. So the black sheep is going to pull these two white sheep. Right? So let's see what happens when the black sheep pulls two white sheep. It's doing something. And one thing that we should note immediately is that these white sheep, they tend to collapse down on top of each other. The white sheep are running the consensus equation, but as long as they're running the same linear protocol, you get the same effect, so it doesn't matter. That's bad from a controllability point of view. If I want to interact with this network, and instead of, let's say that I wake up with the two white sheep on top of each other. If they collapse down on each other, no matter what I do, there's no way I can separate them. Which means I can't go from any point in the state space to any other point in the state space, because there is this subspace where everyone is on top of each other that I can't break out of. If I start there, I stay there. This means that I don't have complete controllability in the control theoretic sense. This is an example of a situation where since I can't separate them, I don't have control over this network. And in fact, you can actually look at the graph without having to compute anything and figure out when do I have control and when do I not have control. So here is this example that we looked at. This is not completely controllable because if these light blue sheep start on top of each other, they're never going to separate, because all they're getting is relative information from the leader, and that information is the same if they sit on top of each other. So they actually never separate. I don't have a completely controllable system. Here's another situation. So let's do the same thought experiment. If these two guys start out on top of each other, they're not going to separate, because they're going to have the same information from the leader, and the relative displacement is 0 between them, so there's no contribution there. So for the same reason, if they start on top of each other, they stay on top of each other, which is another obstruction to controllability. You need to be able to go between any points in order to control a system like this. OK, let's look at this graph. Same thing, right? We place these nodes on top of each other. We add in this node. Maybe we put them all on top of each other. And then the red node starts moving. These two nodes are initially going to be very close, but this guy is going to drag behind. And then, as it has separated, it's going to start dragging this guy behind. So there's actually going to be a separation here. And it turns out that this system is completely controllable. This system I can control all I want. And the key thing here is that there is some notion of symmetry here that's bad if I want to control the system. So it's actually rather surprising that symmetry is not a particularly good idea if what you want is you want to actively interact with your network. So it's just to say completely controllable here. And this idea of symmetry you can actually make a little bit more precise. So here's a graph. Here are the vertices. What I'm going to do is I'm going to just lump the vertices together into cells. So it's a partition, right? So here are the different cells. Now I can define what's called the node to cell degree. So the node to cell degree is the number of neighbors that this guy has in this cell. Well, using this node to cell degree, I can actually build a very particular kind of partition known as an equitable partition. And an equitable partition is such that everyone in the same cell has the same number of neighbors in adjacent cells. We don't have to have the same number of neighbors, but we don't have to have the same neighbors, but the same number of neighbors. So if the three of us are in the same cell, and you guys are in the same cell, and I have one neighbor in that cell, you also have to have one neighbor in that cell. That's what an equitable partition is. Turns out that that's not exactly what we need. What we need is what's called an external, well, what I call an external equitable partition. What it means is that what happens inside cells don't matter. So for it to be equitable, if we're in the same cell and I have one neighbor in this cell, we all have to have one neighbor in this cell. To be an external equitable partition, it means we don't care about the inner workings of the cell, we only care about inter-cell behavior. So that's an external equitable partition. And it turns out that that's what you need to characterize symmetry. So here are 4 graphs. Oh, sorry, yeah, it's 1 graph 4 times. And these are the 4 external equitable partitions that this graph supports. Here's one. Everyone is in the same cell, so everyone has 0 neighbors outside of this cell. Here's another one. Everyone is their own cell. Here's one, right, where the people in this cell have 1 neighbor in that cell. People in that cell, which is a singleton, has 3 neighbors. And here's another one. So these are the external equitable partitions. These 2 are trivial. Right? Every graph has the 2 trivial ones. What I'm going to do is I'm going to call an external equitable partition leader invariant if the leader, in this case the red guy, gets its own cell. So the leaders, where I'm injecting my control signal, are going to be, if you have multiple leaders, I'm immediately going to draw a circle around them and say they are their own cells. Right? So in this case we have 2 leader cells, or leader EEPs. One of these leader invariant external equitable partitions, LEPs, is maximal if I can produce no one with fewer cells. So in this case I have this candidate and that candidate. This is the maximal one because it has the fewest number of cells. And in fact, every graph has guaranteed 1 leader invariant external equitable partition, which is a trivial one. Now, it turns out that this is the structure you need, because now I'm the leader here, I'm the red guy, and I'm moving around. What's going to happen is I cannot control the difference between members of the same cell. That's where symmetry comes in. So if I end up with cells that contain more than 1 node, then I have an obstruction to controllability. So from the leader's vantage point, nodes in the same cell look the same. What that means is that asymptotically, they're either going to collapse down on top of each other if you have a stable, uncontrollable part, or they blow up. But I cannot control the relative displacements inside cells, no matter how hard I try. So that's potentially bad. So what I need to do is I need to build networks or make sure that the robot somehow, if indeed what I want to do is have controllability, then I need to avoid situations like this. So all the followers are running consensus. This, like I said, doesn't matter as long as it's a homogeneous system. The leaders, I'm going to control their positions directly. Then here's a theorem that says that the uncontrollable part, in this case, is asymptotically stable, which means inside cells, things collapse down on top of each other. And the uncontrollable part is given by the difference between agents inside the cells. So the corollary is the system is completely controllable only if the only LEP is the trivial one. I wish I could write if and only if here. It would make me so happy. And for the longest time, I thought I had if and only if, but it turns out that I don't. And there are basically 3 groups who are competing for the if and only if condition. And my view now is that I can't. There is no clean graph theoretic interpretation of controllability that's if and only if. You can get special classes of graphs, but anyway, that's where we are. So we know at least when we can't control it. And now we can go back to this cartoon or this simulation, right, where we saw. Right, so one thing you can do is exactly add gains or weights. And if everyone picks a gain at random with probability 1, you have controllability. So yes, that's something you can do. In fact, that's one way of solving it. What I'm interested in is, and this is why I'm pushing graph theoretic interpretations, is that I would like to have arranged us well, and then Geir shows up a little bit late. I want him to hook in such a way that it doesn't break anything. And that, I don't want him to compute the rank of the controllability gramian. What I want you to do is look around you and say, I'm going to talk to, you pick 3 people and you make sure that you didn't break anything. In your case, I'm not sure I trust that, but anyway, we now know then these are in the same cell. So now we know exactly why they collapse down. I can control the center of mass. In fact, the center of mass inside the cells is exactly what I can control most of the time. But the relative displacement, I cannot. So I think there are 2 morals of the stories here. One moral of the story is if you indeed want to be able to control everyone, then symmetry is not something you should have in your network, which is a little bit counterintuitive. Now, controllability is an awfully strong concept. It means I can go from any state to any other state, which in our case, it means that I can go take all of you and make you change positions with whoever. So let's say I want you to go to a circle. Not only can I move you around in such a way that you all end up on a circle, but I can do it in such a way that I can arrange you alphabetically along the circle. But if you guys are truly homogeneous sheep, the second time I'm insulting the audience, then why do I care about the alphabetical order around the circle? So then you really need something weaker than controllability. So you need, instead of going from a point to a point, you need to go from a point to a set, which is every possible arrangement around the circle. And that's, I think, for homogeneous networks, the right notion. But what we have found is the following things. What we have not found is the pointer. There. So this idea of symmetry is bad if you want to control it. One thing you can do, though, is if you have a graph, it's going to collapse down. And in fact, what you can effectively control are just the cells. So if you have a large network and you want to control it, well, you can actually look at the much, much smaller network and effectively exert control over it. But what I've been interested in now is for robots to move around, and they move around in such a way that they disregard interactions if these interactions render the systems uncontrollable. So here's the sheep herding again. Here's an example now of a controllable system where I'm going to be dragging, this is the leader, and I'll have these intermediary targets, and I'm just going to make sure that I drag them to those targets. And I mean, when you have controllability, in theory, you can unleash the awesome powers of controls. So we can do that. Another thing that one should note when you try to control these networks is the leaders, if they're stationary, if you have a single leader, it acts like glue, right? Because if everyone's running the consensus equation, except Steve was just sitting there, then we're all going to end up on top of Steve sooner or later. It's almost too close for, right? So, by the way, which also makes these kinds of networks rather fragile to hostile takeovers. Because if Steve indeed is having a computer science seminar and he wants all of us to sit in there instead, if everyone's running the consensus equation except Steve, who's slowly walking out of here, then we're just going to follow him like homogeneous sheep to the computer science seminar. So it's a little bit of a fragile from that point of view. But you can actually use this idea. So here is another example with multiple stationary leaders. What happens is that the followers always end up in the convex hull of the leaders. Always. So you can actually use this to do interesting things. There's something known as the containment control problem, where you have big, strong robots carrying toxic waste, and then you have a bunch of agile robots that are supposed to herd them, and you want to make sure that you contain where the toxic waste big robots are. So here, the red ones are the leaders, and they're quickly doing something seemingly semi-random. But the point is that asymptotically, when they stop moving, at least at some point, the followers are going to end up inside of the convex hull. You can actually use this to design these hybrid strategies that have provable containment properties, where you stop every now and then when they get too close to the boundary and let the followers sink into the interior. So you can actually do containment control directly using this. And I want to end actually with another video of a control problem. This is actually a heterogeneous control problem. What I have now is I have two kinds of ground robots and a flying robot. And what I want the robots to do is I want them to go through a series of formations. And the leader is actually, even though it's not physically controlling them, so you don't see the leader doing that, it's doing these weird things in its head. And the followers are actually rearranging themselves. And then you have a flying thing on top of it that's just there to look cool. By the way, this is 250,000 hits on YouTube, so I hope you're... Oh, yeah, never mind. So here's the leader. Here are the followers. So they're going to go through, actually, like the grid thing, a series of formations. And this is where we're doing this homogeneous controllability, where we don't care who goes where on the circle. Which you can handle when you have 4 robots, but if you have lots of robots, you end up with this combinatorial explosion of who can go where. And now you see the quadrotor hovering in the air above it. there is by the way, so you see that the followers have these little things on top of them. So what we wanted them to do was to actually build a mobile landing platform by getting together and then have the helicopter land on them while in flight or while moving, which I think is super awesome. Look at this. Isn't that cool? I think it's fantastic, but and then towards the end, this thing crashes, but it looks like it's landing. So, right, yeah. Here it comes. These quad rotors are pretty amazing. I mean, you can actually, for very cheaply, get things that are reasonably good. They're not super good, but you can have. Yeah, fine. So with that, I actually want to conclude. And what I want to conclude, the first thing I think, the most important thing is the stuff that I did in the beginning, which is basically, if you're going to think about these distributed decentralized algorithms, graphs are, in my mind, the way to go, because if you have to worry about where the mandibles of the ant actually are, then you're going to spend your time on that instead of designing the algorithms. What you need to do, though, is to lift back your conditions on the graph onto the sensing strategies. And then I think this idea of interacting with swarms or groups of robots with leader nodes is interesting. And in fact, I really like this. Just go home and ask your friends this. If you're surrounded by a million robot mosquitoes and you have a joystick, I mean, what do you do with that joystick? I mean, what is fundamentally the right way of making the mosquitoes do something interesting? You clearly don't start dragging individual mosquitoes, because then you issue a million instructions. You clearly don't drag the center of mass, because each robot needs to know where it is relative to the center of mass, which means it has to know a million other positions. What you could do is kind of try to tell everyone what to do, but then your bandwidth becomes ridiculous. So you need something that's fundamentally sound. So figure out what your friends say, and then email me and let me know what the right answer is. I should also point out, of course, that most of this is done by my very talented students. Also, Giancarlo Ferrari-Truccate, Eric Clavins, and Meran Misbahi are my main co-conspirators on this. Again, I listed some of the key, what I consider key results here, or overview papers, in case we list this. And I want to end with a shameless plug for my recent book on multi-agent robotics. And with that, I want to say thank you. I think Morse theory would help me. So I'm going to, in a way, avoid your question, but I'm going to answer a different question. Right? So graphs, we can think of them as what's called one-dimensional simplicial complexes, where you have edges that are connecting nodes. Right? But if I have an edge to you, you an edge to Steve, and Steve has an edge to me, there is a surface there also, which is now a two-simplex. Right? So somehow, if we allow information to be taken into account, not only about the edges, but more things like surfaces, then maybe we can get more information. We could start building higher volumes, for instance. And every time you do that, you get more information. And in sensor coverage, some people have started looking at the problem of avoiding holes by controlling the two simplices, for instance. And I mean, there is more theory lurking underneath this, right? But in general, to go to higher dimensional objects is not a bad idea. I think in general it's a good idea. The one thing, though, is that you have to now endow surfaces with intelligence in a way. Right? So not only do you act at the nodes, but if you involve surfaces, you actually have to have intelligence on edges. And that becomes a little bit complicated if you're going to have to. It's not always clear how you map that onto the individual robots. But the answer is absolutely. The more information you can have, that you're allowed to have, right? And in this case, you're allowed. If I can measure this guy, what is your name? Abdullah. If I can measure where Abdullah is, why shouldn't I be allowed to act, or us together, on this interaction between us? Right? So that information is, if we're talking at least, available. So.
I have that feeling that it will solve it.
All right, good. Okay, good. I like your gut feeling. Okay. So you're the chairwoman here, so.
All right. So it seems like with the grits of letter writing, so instead of being you're talking you can't write EPFL, why not? It seems like that kind of make a rotated version of it or something.
Right. So the one aspect that's cheating about the grits thing is if you want to solve, so if everyone has decided where they're supposed to be in the EPFL logo, and you can somehow measure where you are relative to where you're supposed to be or something like that, then you can do it. Or if you want to solve this who goes where problem in a centralized way, so the who goes where is the assignment problem, and there are cubic time algorithms for figuring out who should go where. You basically sum up the squares of the distances, and you can solve it. But if you truly have 278 robots, there's no way you can do this. And in my case, I had 15 robots. It's pushing it. In fact, what we do is we solve a local version of the assignment problem, meaning this is what the world looks like to me. I'm going to figure out where I'm going, and if there are conflicts, which you can detect because two agents are going to the same point, then I expand the window. And sometimes you actually have to go to all 15 robots. So that's the cheat. And there are greedy solutions to the assignment problem in the sense that, you know what, I'm just going to go to the closest point that's open to me. And you too, but now it turns out that the only available slot for you is way over, it's in Georgia, it turns out. Right, so then you have to, so there are greedy and local solutions that are not so great. And I think that's really the biggest obstruction now is the who goes where problem, not the geometry of it. So the EPFL video was from 2008, actually, and the thing I showed you was 2011. So I think things have happened between, luckily, in the last 3 years. But yeah. I must say, though, that one thing that's infuriatingly annoying about multi-agent robotics is deploying 15 robots, just making them do anything. Making 278 robots do random stuff is actually very hard, because there's always something that's going to go wrong with one of them. So it's still a remarkable feat to run this video backwards. Yeah. So in this case, you didn't. What you did is you had them. The guys that didn't have a leader, they just said, okay, let's maintain this. This was a student solution. That's my guess at what the student did. But in general, the split can't be ensured unless you have an informed individual on each team. And in this case, I didn't. So, but they knew the geometry of the course. So, yeah. So they saw the map, right? Yep.
And how do you abstract? Do you have any comments you can say about how that might map?
So the first comment is absolutely. I think there is something profound going on there connecting to this notion of complexity in computer science. Beyond that, I have no deep insights except that, yes, I agree, and I'm scratching and poking in this direction, but I have nothing as profound as your question to share with you. So. Great question. I wish I had a good answer. Okay, good.
Sorry. Okay, I'll go ahead. Let me just say one more question.
From your simulation, what I see is the graph doesn't have the complete connectivity in the beginning. At the end, it will generate a complete connectivity.
Right.
So in that case, you have a transition matrix which is invariant, time invariant.
Yeah.
So the theory you presented is at the I system. I was wondering how do you extend that to the time varying?
Right, so the theory is extendable to time-varying systems, where you have, so you can find a common Lyapunov function to all connected graphs to the consensus equation. It turns out to be x squared, which is the only common Lyapunov function anyone has ever chance of ever finding. In this case, it turns out that is a common Lyapunov function. So the theory for, as long as the graph is connected at all times, it doesn't have to be complete at all, we're fine. So we have, it is extended to switching networks. But your observation is interesting, is that consensus, in a way, is this universal glue that sucks things down. You have a complete graph. So there are algorithms out there now that takes things, sucks it down, and then breathe. So now we have enough information. Now we go out and do something, and then we. So you can actually inject this into as a way of gluing together different things that you want the system to do. That, you know, we go off and we do things, and then we meet here in an hour, and then we go out and do things again. Right? That's the idea. So the basic theory is extended already to switch networks. But your observation is better than that, that you can actually inject these universal glue controllers like consensus equation. The one thing, though, that if you run the linear consensus equation on a delta disk graph, you cannot guarantee that the system stays connected. So that in itself doesn't maintain connectivity. That's why you need nonlinear weights, for instance, to ensure connectivity. Because you can actually break it into two pieces.
We'll take one last question.
Okay.
Oh, just a fun one, since for those of us into extreme shepherding like you, you mentioned mostly your female sheep. Dogs or the canines, are they aware of that? Do they try to control it?
I have no idea.
Didn't expect it.
So my expected answer is yes, because these aren't random dogs that just show up with a herd and say let's do it, right? Apparently, it's a finely tuned dog-sheep machine, and the dogs actually train with particular sheep for. So my guess is yes, but yeah, yes, yeah. So, but I'm not an authority on sheep herding.
Okay, let's thank Dr. Egerstedt.
Thank you.